Everything we've developed for our cars, the batteries, power electronics, the advanced motors, gearboxes, the software, the AI inference computer, it all actually applies to a humanoid robot.
Tesla redesigned Optimus Gen 3, cutting the number of components by nearly 70% compared to the 600-plus parts in the original Gen 1 prototype. Key sections like the chest, elbows, and knees are now cast as single pieces, or 3D printed, allowing the Giga Press to complete an entire torso module in under 1 minute. So, what exactly in this new design allows Tesla to speed up production so dramatically? Before we begin, please help us reach 9,500 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. How does the new design make Optimus Gen 3 easier to mass produce? Tesla's Optimus Gen 3's design isn't just an incremental upgrade. It signals the birth of a mass production revolution for humanoid robots, a transformation Elon Musk consistently emphasizes as a pivotal turning point for both Tesla and the robotics industry. With plans to produce 10,000 units per month at Giga Texas by late 2025, according to internal Tesla sources and tech media, Optimus has moved beyond a technical demo. It's entering commercial-scale production, much like how the Model 3 helped make electric vehicles mainstream. Musk has stated plainly, mass manufacturing is the real challenge, and if we crack that, the robot revolution begins. Gen 3 was engineered to solve that very challenge. Tesla reduced the mechanical parts count from over 600 components, including screws, micromotors, and joints seen in Gen 1 and Gen 2 prototypes, to under 200 modular or cast pieces, like elbows, knees, and torso, which makes industrial-scale assembly faster and more feasible. As a result, what used to take days of manual work can now be completed in just 2 to 3 hours on automated production lines, with a greater than 98% quality pass rate, according to early 2025 trial runs at Giga Texas. Tesla also applies industrial-grade metal 3D printing for complex components, such as the chest, shoulders, and knees, reducing material waste by about 30% compared to traditional CNC machining, while shortening the turnaround from design to usable parts to just 3 to 5 days. Currently, Giga Texas's 3D printing line delivers roughly 5,000 components per week, supporting its initial 10,000 robot per month goal. Another bold innovation lies in applying Tesla's body-in-white philosophy from the Model Y and Cybertruck, using Giga Press to cast major body structures. Each main torso of Optimus Gen 3 can now be welded, assembled, and painted in under 10 minutes by automated systems, significantly boosting consistency and minimizing human error. Tesla hasn't built a separate robot factory. Instead, Musk is reusing its automotive ecosystem. From welding robots and assembly arms to defect detection cameras and auto-calibration software, saving hundreds of millions in capital investment while speeding up mass deployment. In a company-wide meeting in early 2025, Musk emphasized that Tesla would produce 5,000 robots in 2025 and increase to 50,000 the following year, starting with internal use, then rolling out to customers, with the end goal of creating machines that serve every household. Tesla is betting heavily on its vertical integration advantage, from 4,680 battery cells and power electronics to the shared AI between its cars and robots, as well as its homegrown automation software. Optimus Gen 3 is not just a new robot, it's a symbol of industrial scalability. According to Digital Habitats, if Tesla reaches 1 million units per year, production costs could drop below $20,000 per robot, and possibly as low as $10,000 with continued scaling. This vision drives Tesla's constant refinement of the Gen 3 design, with each engineering tweak aimed at lowering costs, simplifying production, and maximizing replicability. In a Twitter post shared by Musk, he proudly declared that Optimus will be the biggest product in history, and projected 500,000 to 1 million units could be produced by 2027, forming a new labor force far beyond traditional machines. In this landscape, Gen 3 is no longer a lab-bound prototype, but the production-optimized model designed to turn the idea of a large-scale robot factory into reality. If Tesla maintains its current speed and precision, Optimus Gen 3 could become the first humanoid robot ever mass-produced at million-unit scale, a milestone no competitor has reached. And more importantly, it will prove Musk isn't just making bold promises, he's delivering the robot revolution in real time. Once again, please help us reach 9,500 subscribers. This is important for us to stay motivated. Thank you. How is Tesla leveraging existing production lines to build Optimus Gen 3? Tesla didn't build an entirely new factory to produce the Optimus Gen 3. They turned their massive existing car plants into production sites for humanoid robots, leveraging a decades-built ecosystem of automation technologies. This sets Tesla apart from top names in robotics, like Boston Dynamics, where Tesla simply uses automotive production lines, including welding robots, assembly arms, and the Giga Press, to make a humanoid robot, while Boston Dynamics still relies on manual assembly and high production costs. Elon Musk told employees that by 2025, Tesla expects thousands of Optimus units running in Tesla factories by the end of this year and expanding faster than any product in history to millions of units per year. This is more than symbolic rhetoric. It's a technically grounded goal as Tesla continuously adapts its Giga Texas and Fremont plants, fully equipped with automation, welding, painting, and quality inspection systems, to produce robots instead of building a completely new production line. Rather than investing in a separate robot factory, Tesla reprogrammed the software of its existing welding robots to handle Optimus's mechanical components. For example, robots that weld vehicle frames now weld the hip and thigh joints of Optimus. Paint booths apply coatings to robot frames, and surface inspection cameras that screen automobiles now inspect a robot's wrists and knees. Tesla's full self-driving FSD software, which powers image recognition and decision-making in cars, is reused to control Optimus's sensors and cameras, saving the cost of developing entirely new robot software. Meanwhile, Boston Dynamics, known for Spot and Atlas, continues manual assembly with specialized expensive components. While Spot costs around $75,000 per unit, Optimus Gen 3 is targeting just $20,000. Atlas, once a showpiece, still costs hundreds of thousands per unit and hasn't reached commercial mass production. Tesla also uses the Giga Press, an immense press that can cast a vehicle frame every 80 to 90 seconds, to manufacture Optimus components. The torso or back sections of Gen 3 can be cast in one piece, enabling fast welding and assembly. According to internal Tesla test data, each assembly takes less than 10 minutes. Moreover, Tesla reuses more than just hardware. They've also adapted software proven in cars, fully utilizing sensors and FSD chips for robot vision and decision-making. Competitors like Boston Dynamics must develop new software and integrate LiDAR systems and custom AI from scratch, significantly increasing recurring costs. Tesla is even testing production within its factories. In mid-2024, 2 Optimus Gen 2 units were trialed on an assembly line in Fremont, performing simple tasks like component handling. This real-world testing alongside other Tesla robots and human workers demonstrates the feasibility of factory-first deployment. By contrast, Boston Dynamics and startups like Figure still depend on specialized production lines, often dispersed and not scalable. Robot prices between $30,000 to $150,000 remain out of reach for mass markets. Even Figure AI, backed by Amazon and OpenAI, hasn't reduced per-unit costs below $50,000 due to small-scale production setups. In summary, Tesla is executing a full A-to-Z strategy in its existing manufacturing footprint: robots, presses, electronics, AI software, and FSD. This strategy saves hundreds of millions in capex and accelerates mass production far beyond what Boston Dynamics or other startups can attempt. While competitors struggle to reduce each component's cost, Tesla already controls the full suite: equipment, software, technicians in its Giga factories. They didn't start from zero. That's why Musk confidently forecasts thousands of Optimus units working in Tesla factories by year-end, rapidly scaling to hundreds of thousands annually, far surpassing competitors. Tesla isn't merely talking about technology, they are deploying it, proving that their deep integration strategy and economies of scale aren't just bold, but real. And it's this difference that will define the future of global robotics. How low can the price of Optimus Gen 3 go thanks to the new design? One of the biggest questions surrounding Optimus Gen 3 is, can Tesla drive down the price of this robot enough to make it a mass-market consumer product? All of Elon Musk's recent signals suggest this isn't just possible, it's the core of Tesla's commercialization strategy. Musk has emphasized that Optimus's cost must be lower than the wages of human workers in developed countries. Speaking with shareholders, he estimated that production cost could drop below $20,000 if optimized well enough. That's staggering when compared to existing robots like Boston Dynamics' Spot, around $75,000, or humanoid prototypes such as Figure 01, around $100,000. Hitting that price target demands a dramatic redesign, eliminating unnecessary parts while ensuring uncompromised reliability and safety. On Gen 3, Tesla has dramatically streamlined its design compared to earlier prototypes. Leaks and demo videos from Investor Day show it's about 10 kilograms lighter and uses 30% fewer mechanical parts. Reducing parts accelerates assembly, trims costs for spare parts, quality control, and inventory, all major contributors to mass production expense. Material costs have also shifted significantly. Tesla appears to have moved from standard aluminum and steel to cast alloys and reinforced polymers on some external components. These materials are cheaper, lighter, and easily produced via molding or 3D printing, especially at scale. Industry experts estimate that reducing the robot shell from dozens of components to just 4 to 5 major pieces could cut material and machining costs by over 40%. Another direct contributor to lower cost is Tesla's reuse of automotive hardware and software. The FSD chip powering Optimus is identical to the one produced in hundreds of thousands of Tesla vehicles annually, saving tens of millions in development versus building a new processing chip. Cameras, sensors, and electric motors are drawn from Tesla's auto supply chain, the same one that gives the brand scale and cost advantage. Internal production sources suggest that with a volume of roughly 500,000 robots per year, the manufacturing cost of Optimus Gen 3 could drop to around $14,000 to $16,000, already cheaper than a standard Model 3. If bundled with subscription services or integrated into smart home packages, retail pricing might come in even lower than the $20,000 Musk pledged. Business model plays a key role in pricing strategy. Tesla doesn't need high-margin hardware sales to profit immediately. Like with the Model 3 and Solar Roof, they could sell the robot near cost and recoup via services, software updates, or AI-powered subscription packages. For example, Optimus as a service could let customers rent the robot by the hour or monthly to assist with home chores, elder care, or meal prep, capturing long-term revenue well beyond hardware sales. The target market reinforces this strategy. For industrial or factory use, a $50,000 robot would be acceptable. But the Gen 3's lighter, softer design targets household consumers, families with elderly members, special care needs, or professionals wanting in-home AI assistance. Only a sub-$20,000 price, perhaps financed monthly, could make a humanoid robot as accessible as a smartphone. Tesla's vertical integration gives it an advantage no competitor can match. Boston Dynamics has tech but lacks automotive-scale factories. Figure AI relies on third parties. Agility Robotics, despite Amazon deployments, still can't undercut $40,000 per unit. It's surprising just how practical Optimus Gen 3 has become. Its outer shell can be swapped out on site in just a few minutes. Even more impressive, it lasts up to 10 years, slashing long-term maintenance costs. With a fully modular design, the robot stays ready to operate around the clock, even in demanding environments. So how exactly was this shell designed to deliver durability, flexibility, and mass deployment capability all at once? Before we begin, please help us reach 9,500 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. What technology has Tesla applied to the outer shell of Optimus? One of the key factors helping Tesla's Optimus Gen 3 move closer to real-world application and large-scale production lies in its outer shell design. a component that may seem simple, but plays a decisive role in durability, weight, cost, and operational safety. Unlike competitors that still rely on heavy, rigid, or expensive industrial metals, Tesla has brought advanced material technologies from the electric vehicle sector into Optimus Gen 3. Accordingly, the shell of this new generation robot is made from ultra-light polymer composites, likely engineering plastics reinforced with carbon or glass fibers, allowing for flexible shaping, low weight, and high durability, similar to the materials used in the frame and interiors of the Tesla Model Y or Cybertruck. This is particularly important considering Elon Musk's target of keeping the total weight of Optimus Gen 3 under 123 pounds, which is nearly 30% lighter than existing humanoid robots on the market, such as Figure 01 154 pounds, or Boston Dynamics Atlas 196 pounds. This marks a significant leap from the previous two generations. With Optimus Gen 1 introduced in 2023, the outer shell was purely symbolic. It was mostly made of hard plastic or foam to simulate a humanoid form. By Gen 2, introduced in late 2022, Tesla began real-world trials with the robot, and the shell was upgraded to stronger materials, such as engineering plastics or lightweight alloys. However, the design was still fairly crude, with many components manually assembled, not optimized for mass production. The shell was still relatively heavy, putting stress on joints and motors during operation, increasing energy consumption and limiting battery runtime to about 1 hour per charge. By the time Gen 3 debuted in early 2024, Tesla had made a major leap in both design and materials. The outer shell of Optimus Gen 3 features a seamless modular structure with tightly integrated panels that can be easily detached individually for maintenance or replacement. The polymer composite material reduces total weight by approximately 26 to 33 pounds compared to Gen 2, while increasing impact resistance and corrosion protection. The exterior is surface-treated using powder coating or industrial-grade film wrapping, similar to the finishing processes applied to Tesla's electric vehicles. This gives the shell anti-smudge, anti-static, and scratch-resistant properties, ideal for industrial settings and indoor environments alike. Tesla also applies advanced manufacturing technologies to the robot shell production process to optimize speed and cost. Specifically, the panels are formed using injection molding or vacuum forming to ensure precision, reduce material waste, and shorten production time. These methods, already used by Tesla for years in the EV industry, are now repurposed to accelerate the commercialization of Optimus. It's estimated that a complete shell for Optimus Gen 3 can be produced in under 2 hours, compared to dozens of hours if built manually like many of its competitors. Additionally, Tesla's use of automated paint lines, similar to those for the Model 3 or Model Y, helps reduce surface finishing costs to only about $50 to $80 per robot, compared to $200 to $300 for manual painting. All these innovations in the outer shell bring numerous practical benefits. First, regarding weight, the new materials reduce strain on joints and actuators, allowing the robot to move more efficiently and conserve energy. For a robot operating throughout the day on a battery with a limited capacity of around 2.3 kilowatt-hours, reducing just a few pounds from the shell can extend runtime by 30 to 40 minutes. Second, in terms of safety, the polymer composite shell has no sharp edges, is non-conductive, and absorbs impacts better than metal, making it especially suited for environments with close human interaction, such as homes, hospitals, or offices. Third, it offers aesthetic appeal and customization. The unified, glossy finish can be painted in various colors: white for healthcare, gray for industrial use, black for security, enabling Tesla to easily tailor the robot to specific uses and markets. Compared to competitors like Boston Dynamics, whose Atlas robot uses a complex heavy metal shell, or Figure AI, whose design is not yet optimized for high-volume manufacturing, Optimus Gen 3 stands out for its balance of performance and scalability. A lighter shell means lower transportation and assembly costs. The modular design allows for rapid maintenance without disassembling the entire robot. The flexibility in form and surface finish gives Tesla the ability to adapt the robot's exterior for each specific version, a capability that very few robotics companies currently possess. Once again, please help us reach 9,500 subscribers. This is important for us to stay motivated. Thank you. What are the practical applications and benefits of using this type of shell? One of the key factors helping Tesla's Optimus Gen 3 move closer to real-world applications and mass production is its outer shell design, a part that may seem simple but actually determines its durability, weight, cost, and even operational safety. Unlike competitors still using heavy, rigid, or expensive industrial metals, Tesla has brought advanced materials from the electric vehicle industry into Optimus Gen 3. The outer shell of this next-generation robot is made from ultralight polymer composites, possibly engineering plastics reinforced with carbon fiber or fiberglass, allowing flexible shaping, low weight, and high durability similar to materials used in the frame and interior of Tesla's Model Y or Cybertruck. What are the economic advantages and surface finishing methods? In the race to develop humanoid robots, success depends not only on AI brains or actuation systems, but also on factors that might seem cosmetic, like the outer shell and surface finishing process, which play a critical role in cost, production speed, and market readiness, and Tesla fully recognizes this. While competitors such as Boston Dynamics, Agility, Robotics, and Figure AI concentrate on mechanics and motion, Optimus Gen 3 is designed with a philosophy that optimizes the entire supply chain, from hardware to aesthetics, to serve mass production. And the shell isn't just a shell, it's part of a strategy to bring the robot to a mass market price. One major difference lies in the shell manufacturing and finishing process, where most competitors still rely on powder coating or manual paint application, which are labor and time-intensive. Tesla has fully automated the shell painting line using the same technology applied at its automotive plants like Giga, Texas. As a result, each Optimus Gen 3 shell is fully painted in under 7 minutes, with less than 0.1 millimeter variation in coating thickness per layer, and the robotic painting system can adjust color, gloss, and UV protection in real time, ensuring near-perfect consistency across thousands of units. Beyond speed, Tesla has completely eliminated manual polishing, a common step among high-end robot builders like Apptronik and PAL Robotics, and instead employs a 2-layer semi-self-healing coating, a flexible base layer that absorbs minor scratches, covered by an outer layer that resists dust, water, and fingerprints. This technology not only keeps Optimus looking new longer, but also cuts surface finishing labor costs by 85%, which is enormous when scaling to hundreds of thousands of units per year. Another distinction is that Tesla fabricates all its robot shell molds in-house using fast-turn tooling, rather than outsourcing like most competitors, enabling design iterations in days instead of weeks. For example, creating a mold for a wet environment variant of Optimus might take just 72 hours, while others could require 3 to 5 weeks, giving Tesla unmatched adaptability to market demands. On the material cost front, most rival companies still use lightweight metal shells, aluminum or alloy, or premium imported plastic injection molds that are expensive to produce, require multiple finishing steps, and are hard to recycle. In contrast, Optimus Gen 3's shell is designed for on-site recycling. Old or defective shells can be ground up and reused in future production runs, reducing raw material costs by 15 to 20% and aligning perfectly with high-volume manufacturing needs. Tesla also avoids permanent color finishes, opting for plain black or gray shells with high-grade industrial decals for customization instead of full repaints. At just $5 to $20 per decal, companies can rebrand robots quickly without retooling or voiding warranties. This is foundational to the robot-as-a-service model Elon Musk has proposed, where a single robot can change roles in hours. For instance, adapting from an Amazon warehouse shift to a hospital care assignment simply by swapping its outer panels. This level of flexibility is unmatched by competitors with monolithic shells or limited customization. Tesla also addresses environmental and depreciation concerns. Minor scratches or fading can be corrected by swapping covers rather than repainting, which saves chemicals, labor, and time, enabling cosmetic renewal in under 10 minutes at a material cost under $50. far lower than resurfacing costs at other firms. Finally, the biggest benefit of all these innovations is that Tesla can bring the shell finishing cost of Optimus below $300 per robot, while competitors typically spend $500 to $1,500 due to manual processes or expensive materials. When multiplied by a target production volume of 100,000 robots per year, this cost saving amounts to tens of millions of dollars, without sacrificing quality, durability, or aesthetics. What are the practical applications and benefits of using this type of shell? Another advantage lies in the robot's ability to integrate with various industries without structural changes. The Optimus Gen 3 shell serves as a modular interface, allowing easy attachment of specialized equipment, branding, or additional sensors. For example, an airport service unit could feature a flight information display on its chest, while a hotel version might be decorated with the brand's logo, LED accents, or earpiece for communication. Because of its straightforward yet flexible design, Tesla doesn't need to redesign the robot itself for each use case. Just swap shells or add peripheral components, significantly reducing both vertical deployment costs and lead times from pilot to real-world rollout. On a daily operational level, the modular shell design delivers substantial advantages in maintenance and uptime. When robots are expected to run several hours a day, such as in factories, warehouses, or hotels, minor scratches, dents, or surface damage are inevitable. Tesla accounted for this upfront by designing the shell panels for quick, tool-free replacement, eliminating the need to disassemble the entire robot. Technicians can address cosmetic damage or surface wear within minutes, without affecting internal components like motors, cameras, or control circuits. Additionally, the shell is resistant and lacks small crevices where dust can accumulate, making daily cleaning as easy as wiping with a damp cloth or using a light blow of compressed air. This significantly reduces routine maintenance time, crucial for enterprises operating dozens or hundreds of robots simultaneously. From a financial perspective, the shell design also helps Tesla optimize total cost of ownership. One of the biggest challenges facing humanoid robot makers is the high cost of post-sale maintenance, often exceeding initial purchase prices. But with easily replaceable shell panels that do not interfere with internal systems, the robot's overall lifespan can be extended dramatically. Materials experts estimate that Tesla's polymer composite shell lasts an average of 7 to 10 years under regular operation, similar to the lifespan of high-grade automotive plastic cladding, which means even with daily operation of 8 to 10 hours, an Optimus won't need a full shell replacement for many years. Instead of shipping robots back to central factories for repairs, Tesla can offer field replacement service or ship parts to customers by mail, an after-sales business model similar to laptop or printer support, saving customers significant cost and downtime. Tesla also addresses regional market demands and cultural expectations through localized shell variants. Using a flexible production line, it can customize Optimus's appearance, such as offering friendly, bright exterior styles for Japan, minimalist and utilitarian versions for Europe, without changing core internals. This localized customization, enabled by detachable exterior panels, gives Tesla a competitive advantage in rapid global deployment. Last but not least, the modular shell becomes a foundation for scalable product diversification. With interchangeable molds and small design changes, Tesla can offer basic, mid-tier, or premium versions without overhauling the entire tooling process. For example, a lightweight domestic version can skip advanced finishes and cost 20 to 30% less than enterprise-grade iterations, while a high-end, water-resistant, self-healing nano-coated version could serve medical, security, or military sectors. The robot's outer shell has become an open design platform, allowing Tesla to segment offerings similar to the strategy used for Model 3, Model Y, and Model S in the electric vehicle line. We appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno Creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.